following theorem can be conveniently used to calculate the responses in the 20 ohm resistor. Thevenin's theorem, Milliman's theorem, maximum power transfer theorem, superposition theorem. Okay, if you observe here, he has given this source is operating at frequency omega 1, whereas this voltage source is operating at frequency omega 2. Since we have energy storage elements, inductors and capacitor, these are frequency sensitive. Okay, when you have frequency sensitive of different frequency sources are connected, so we have to use superposition theorem. Why superposition theorem means we will take superposition theorem only one source at a time, whether it may be current source or voltage source. So these frequency sensitive elements will respond to only one frequency at a time when one source is acting alone. Okay, that's why these three theorems we should not use. We should use only superposition theorem, since we'll consider only one source at a time and total response is equal to summation of individual response of each source. So superposition theorem, option D is the correct answer. The following figure, find ammeter A reading. Okay, we have four ammeters here, ammeter A1, A2, A3 and A4. We have to find ammeter reading A. Okay, now if you see here, ammeter A1 is connected in R branch, since these four branches are parallel across 100 volts source. Okay, now what is the current? Let us take ammeter current reading as I1. This is the voltage V, which is equal to 100 at an angle 0. I1 will be in phase with V. I2 will be lagging by some angle, because since this is inductor, current lags voltage by exactly 90 degrees. Ammeter 3 reading, let us take it as I3. Since it is connected with capacitor, the current is I3 is leading by 90 degrees with respect to source, whereas I4 should be in phase with I1. Okay, so this is I4. Now ammeter A1 reads 2 amperes, A4 reads 6 amperes. Now what is the resultant current which is in phase with voltage source? 2 plus 6, which is equal to 8 amperes. Similarly, ammeter A3 reads 18 amperes. Okay, A2 reads 12 amperes. That means this is resultant is equal to 6 amperes in upward direction. Now what is the ammeter A reading? Ammeter A reading is resultant of these two. Okay, what is resultant of these two? I is equal to 6 square plus 8 square, which is equal to 10 amperes. Option B is the correct answer.
The bandwidth of two-stage tuned amplifier with each stage having a bandwidth of 1 MHz. See, in case of if we are cascading two stages, means the gain is going to increase. We know that for an amplifier configuration, the gain bandwidth property is going to be constant, so bandwidth is going to decrease. The new bandwidth, that is equals to 2 power 1 minus n under root into bandwidth of each stage. That is, here n is equals to 2. So 2 power 1 minus n under root is equals to 0.643. When the bandwidth of each stage is 1 MHz, so new bandwidth is 0.643 MHz. That is, option B is correct. On sample, the electron concentration drops linearly from 10 power 18 per centimeter cube to 10 power 14 per centimeter cube over a length of 4 into 10 power minus 4 centimeters. The current density due to the electron diffusion current is dn is 35 centimeter square per second. So current density Jn is nothing but Q dn by dx, which is nothing but Q is here into 10 power minus 19 into 35 minus Q. This is electron charge is negative, as well as dn is also negative here. So 10 power 14, 10 power 8, and this is 4 into 10 power minus 4, which is nothing but which is equals to 1.4 into 10 power 4 amps per centimeter square. That is, option C is correct. input and low output impedances of a feedback amplifier, the topology use this. Here series kind of connection. See, first parameter always, that is the parameter towards the output side, and the second is these and this is the first, this is second. So in order to get low input as well as low output impedance, the output must be connected in shunt and the input must be connected in shunt. That is, if we are connecting output in shunt, means we are taking the voltage as we are sampling the voltage at the output side. That is, voltage shunt is the possible topology to get both low input as well as the low output impedances. That is, option D is correct. In values, we have to find out the ICQ and VCEQ. Beta is given as 100 for the following circuit shown below. So here VB is written as, here VB is 24 divided by 20 into 10 that is, sorry, here VB is going to be 0 because of the exactly opposite and equal potentials. So, and Thevenin's resistance is going to be 5k. So if we model this circuit as, this is 5k minus 12 ohms, 2k plus 12 ohms. So apply the KVL at the input side. 0 is equals to IB into 5 plus VBE, that is 0.7, and 101 IB into 2, and plus this is minus 12. So 12 is equals to 207 IB plus VBE, that is IB is equals to 12 minus 0.7 by 207 milliamps. So ICQ is nothing but beta times, that is 100 times 11.3 divided by 207 milliamps. So VCEQ is equals to 24 minus ICQ 4. So from this, ICQ and VCEQ is given as, here this is nothing but 5.459 milliamps. VCEQ is nothing but, it is, so 5.46 we can take approximately. This is 2.04 volts, that is option D is correct.